pleasure to have Doan today. Doan is a postdoc in the University of Freiburg. He works in the embedded model predictive control group there. And he has done his PhD at Delft University in the Netherlands, where he was working with Bart de Scooter. So Bart works with Georges Lacour here, I think. I don't know if there's anybody from this group. So he worked on distributed VPC at the time. And so then afterwards he went back to Vietnam for 2 or 3 years. He was a lecturer there, and so now he's a postdoc in Europe. And so he's interested in MPC originally, but also, of course, in all the things that go with it, including in particular optimization and distributed convex optimization. So we look forward to the talk. And, so you have about maybe an hour.
Very generous, thanks.
What's that?
Yeah, very generous. Thanks. I'm very happy to have a chance to visit Montreal and listen in Congo, Opera, so that we have some people here. I work in the field of control and optimization. My group now is in Freiburg, and this is the bigger department where they call centralized impact when their major strength is in macroeconomic system in the domains and they do a lot of sensor stuff. When my professor is one of the isolated groups there, but he just started recently. He worked mostly control and optimization. I have learned from the Institute from Google, which is very nice. That supports me to stay for 2 years in Germany, and that 2 years I had a lot of ability to pursue my research in connection with the host group. So if you guys, some of you are doing PhD and you also want to consider, you have 4 years after your PhD to consider applying for a fellowship from Alexander Foundation Foundation to come to Germany. And this is after my talk, we will introduce a little bit more about my group, myself, and then I describe the optimization problem and where it comes from the control problem, and then I will talk about the algorithms to solve it. So the group name is System Control and Optimization. The professor Maurice Bill, originally he comes from the University of Heidelberg. So in a big group in mathematical science and control and optimization. Then he started his career in KU Leuven in Brussels, and from 2013 he moved to Freiburg. These are the main research focus of the group. We expertise in sequential cooperative programming to be used to solve the analytic nonlinear programming problem in control in MPC. And in my group, then we are racing with the other group in real-time MPC, where we aim for sub-millisecond sampling rate. And the MSE, which is the moving horizon estimation, is the dual problem of MPC, where in MPC we aim for control, with MSE we aim for estimating the state. We are also working on embedded optimization to create the solver for embedded system, and also to implement them on the real system. One of the big applications is renewable energy, where we have the systems, we have the theory and also also practical work on using the kite, flying around kite to generate power. And now they are moving a little bit toward prototyping and testing phase. We are also expanding to some mechanistic system like motor control or interbike control. Currently, I also have Wi-Fi in Doan. See the group. Currently, we have Professor Dio, and we have three postdocs. And below Professor Dio, there are I think 7 internal PhD and some external PhD. They work around Germany and also Netherlands. Focus the external one. They focus more on applications, and internally we have also some people working on some practical system. But most of them they also do some typical research. I think the team.
What's an external PhD? Somebody who works in a company?
Some of them work in company like these two guys. They work in a startup company in kind energy. So they do modeling, simulation of the kind, and then apply some control for trajectory planning and also tracking the trajectory. These people they come from the Hochschule, which is kind of, I think it's now they compare to the ETS one Econ Technique Superior, is it? Here in Montreal, so they do more apply stuff. But when they are in those schools, they don't. Their school cannot provide the PhD degree yet. So their supervisor also have contact with Professor Dios supervising as well in the methodology. And these are the major product till now. We are developing different software packages. These three major software packages that Professor Liu has guided students to develop during his career. The Aikido one that have to formulate MPC and MHE problem with their MATLAB interface is also very simple to use. And one good thing is that it can generate, so when we formulate the MPC problem, it can generate a C code. With the C code, we can, this is a self-contained C code that they can be implemented in different embedded systems. As far as they can compile the C code. And the Kasadi one is it is now being considered very fast in providing the derivatives of the functions. So let's say when we do MPC or different optimization problem, there are some techniques, many techniques based on using the gradients or Hessian. So by computing derivatives in some numerical way, what we call automatic differentiation, it has to provide those first order or second order derivatives. And Cassidy helps us to formulate the MPC problem very, very easy, very simple. Now we can write 10 lines of code to formulate the problem and also to ask the solver to solve it. Recently, we have a postdoc coming from Denmark. He developed the plus field with the plus is basic linear algebra routing. So focus on solving the linear algebra problem in embedded system. No, not really focus on the system, but he provide different customization for different platforms. Like we have support Intel Sandy Bridge, Intel Haskell, or some microcontrollers or microprocessor architecture, very fast one, and we will use this Haskell a lot to develop our embedded MPC applications. For myself, I have done my PhD in distributed and hierarchical MPC. And distributed thing is that we have peer-to-peer processor to solve the problem. And hierarchical thing is means there are different layers. The top layer control the second layer or symbol go downstairs. And since I got my PhD in 2012, since last year I started in the lab in Freiburg, and my research focus right now is in digital optimization, which is based on convex optimization and the application of optimization in control like MPC, MHD, and I'm using our software package in that system like the context M4 or the ESP32 microcontrollers. Now, when I go to so the problem that I want to discuss here is a large-scale complexity problem. Large scale means we can face the problem with hundreds or thousands or more of subsystems. And the problem is like this: that we have a convex cost function, which is the sum of some local cost function fi, and there are some constraints which can couple the variables together. These are general inequality constraint, general equality constraint. The variable x is composed of the variables coming from different subsystems, from xn1 to xn with m subsystem here, and the constraint set calligraphic x here is just a simple set merged from the local constraint set. So xi is the set xi, but these constraints really cause the problems in solving this optimization problem. And why they are problematic? Because they are coupling on around across different subsystems in this constraint in the G and H. And solving this is rather difficult, and especially when we have the large scale problem. By the way, some people who work in machine learning also see this problem very, very frequently, but often these constraints are not in that problem. Machine learning until now, most of the problem now deal with constraints, but for MPC we have such constraints, and my task is try to deal with such constraints in this convex problem. But we also assume that we have some sparsity structure. For example, this fi, while I write that it depends on the whole variable x. Indeed, it just depends on some local variable. Xi is the variable of subsystem I, and x of ni this represent that the variables inside the neighborhood of xi. This is like.
So you mean the whole thing is convex? So
G can be convex, but in this for now, this is a framework that I'm trying to generalize it, but my main focus now is when G and X, they are linear amplified functions. The task is certainly we need to deal with it in a distributed way because the problem is large scale, and because MPC there is one different thing than the other optimism problem is we often always need to maintain the feasibility, which means every solution that we get, even if it is not the exact solution, it should still be feasible. Because of that requirement, the feasibility requirement, the other method using dual decomposition often doesn't work. Yeah, we are dealing in the convex case, so we can use dual decomposition. However, when we solve the dual problem, but it does not provide the exact solution yet, then such solution is not guaranteed to be feasible to the original problem. So but there are also a lot of work in distributed MPC. They deal with such dual decomposition, so they solve the dual problem and they assume that the algorithm will obtain the exact solution, and then because they can transform that into the solution to the primal problem, they can use it. Indeed, I also have a paper in that medicine as well. But then, now let's say if I only have approximate solutions, then using dual decomposition technique is not good for feasibility. So my main focus now is to use primal decomposition, which means just solve the origin of the primal problem, don't solve the dual problem. And solving the primal problem, there are different techniques as well, like ordinary descent, for example. And my approach here is to use the Jacobi algorithm. I will present the algorithm later. So this gives motivation examples of people see where this problem comes from. Let's say I have different subsystems, a network of subsystems like this, or they are like a lot. They have dynamical couplings. Let's say the state of one subsystem depends on the state of the other subsystem actually in the neighborhood and the control of the other subsystem. And also there are some operational constraints that limit that couple them together. Here we will only consider the affine constraint, linear constraint. For example, let's consider the subsystem number 3 here. Let's say I have the dynamical coupling between 3 and 4, which means the state of subsystem 3 will depend on subsystem 4. And also I have some couple constraints that link some state of input between 3 and subsystem 2 and 5. Then I would say the neighborhood of 3 comprises the subsystem itself and the other one that influences it. And the assumption is that for every subsystem we have a local controller. So this controller, they will need to communicate with each other in order to solve the whole centralized problem. Any question here? So in short, I have one local controller for each subsystem, and because of the existing coupling in the dynamic and the constraint between them, that there must be some local communication link between the controllers, so they will exchange information during the course of solving this problem. not familiar with MPC, I will just provide general description. Let's say this, let's look at this plot. I am now at the time step K, and I want to find a solution. I will find some good control in this time step. Say from K to K plus 1 is in discrete setting. In order to get something which can be considered good or optimal, I would formulate an optimization problem where I will look at the n step ahead, like they call it horizon. In this horizon, like from K to K plus n, I will formulate an optimization problem and I will solve it. After I solve it, I will get some optimal solution which comprises of the predicted control, the blue line, and associated with this predicted control, I have the predicted state, the red line, for example, the predicted state here, the blue line, for example. And when I solve it online and I get the solution, I will apply only the first step. So I will apply only the first step control. And after the first step control, the system will measure or estimate the state again. The blue one is what I predicted at the time step K, but because of some noise or disturbances, uncertainty that my real new state, the red one is different, not like the one I predicted at the last stage. So at this time step K plus 1, the whole procedure is repeated. I will look at the horizon from K plus n to K plus n plus 1, and then I will do such optimization problem solving again and apply the next control step, control input, so that just continue rolling up to the future. By using the philosophy that transforming all of the control task into optimization, it helps us to deal with different things, like if there are some constraints, like we have maximum minimum input, or we have maximum minimum state limit for the state, we can just put them as constraints in the optimization problem. So it's quite simple to deal with constraints. And we also deal with MIMO system very easy. It's not difficult if we want to go from SISO to MIMO system. And we can also add some terminal constraints. It is used to guarantee stability of the control. And also initial condition is another constraint for this problem. So then every sampling step I need to formulate with the sampling step. Let's say I want to solve it within 100 milliseconds. So the idea is somehow in less than 100 milliseconds I need to solve the problem and get the solution to this MPC. More in formulation like this, I try to keep things simple as possible, but still cannot avoid using those indexing. So let's try to provide some very simple one. This is cost function, which basically says what do we view as the optimal thing that we want to optimize, the objective function or the loss function. And often in MPC we use quadratic cost function. And if we have Q, R, and P, these are only positive semi-definite matrices, then this cost function is convex cost function. And if any of those put the positive definite, then we have strongly convex constraints. Now, in these constraints, they are only affine constraints. And so if I have the system with linear time invariant dynamics, then the whole problem is a convex problem. Now if I go to distributed setting, I say my state consists of the state of M subsystem. My input consists of the input of M subsystem. And I have a couple of dynamics that provide some coupling between them and that help me to show that the state of one subsystem, how it depends on the other state or the other input. Then we put these formulation in the MVC problem, and also we need to do some reordering of those vectors. Then we will obtain the original the Jacobi problem that I presented before in the first form. So quite general convex problem with in this case we only deal with the phi, g, and x function. And then the optimization variable bone x is comprised of all of the state and input of all of the subsystems. Like I have a subsystem from 1 to subsystem n is quite huge vector. But indeed, we don't. When we solve it, we need to avoid dealing with this centralized vector variable because it's quite big. If we consider large scale problem, it should be quite big. Not good to store in the memory or not good to deal with in some operation when solving it. The idea is if I can decide some optimization algorithm that only, let's say, only deal with the local state and input, the local variables, it would be easier to implement. So that is the motivation to go to distributed optimization algorithm to solve such problem. Let's talk about the background of Jacobi algorithm. In the book of Vestergaard and Sixlist in the late 80s, they did a book parallel and distributed computation. They describe, they summarize the Jacobi algorithm like this. Let's say I have the minimization of this problem, where also it depends on the state of the variable of different subsystems on the large scale as well. The idea is each subsystem only minimize the problem with respect to xi, the variable of the subsystem I, while for the other variable, they consider that those variables just stay at the previous step p, and this is iteration p plus 1. So let's say if this is iteration p, each subsystem is represented by one process like this. Each one only optimized for the variable itself, while consider the other one still stay at that previous step. And after they optimize, they can exchange information and say, hey, this is my new solution. I will send my new solution to the other process, and the other one will update it, and they just continuously resolve it. And there are the analysis showing that this scheme guarantee to converge, and they also provide convergence rate, like geometric convergence rate. And this is quite simple to do in parallel. If we have a mechanism to send the update of the newly found variable to the other processes. And there are different variations of algorithm as well. So here I only provided the very basic one, which is called the synchronous one. there's also the asynchronous algorithm where when one system finishes, they don't need to wait for the other one. Let's say if this one finishes first, they may just continuously update the information and resend and resolve the problem. But here the synchronous one, they need to wait until everybody finishes, and there's some syncing between them to redo the process. However, in this algorithm, there's only analysis for the case when there are no couple constraint. Let's say the x, the constraint set x is just a hyperbox, or we call the Cartesian constraint set, which means that it can be considered as unconstrained problem. But when
I'm trying to understand
yeah.
the picture here, because the algorithm that you show here, it seems that the agents are updating one at a time. Like here, it seems to me from what you write, it seems that all of the other ones are fixed except I.
Yeah.
And then I minimizes.
Yeah.
The other one's fixed. But when you show the picture here, it seems that, so for example, that they are all optimizing in parallel.
Yeah.
So that at the next update, it's not going to implement.
Exactly. So in the next update.
Because at the next update, when they start the second round,
yeah.
For example, the first one will receive the information based on all the other ones having the data as well.
Yeah.
So it's not exactly the same.
In this,
I mean, to me, that would correspond to a picture where you have blocks one at a time.
Yeah.
And you do it periodically.
This is not the same problem as my problem.
No, I'm trying to see the correspondence between the algorithms that you have here.
Yeah.
And you were saying it's the same thing as what you showed in the picture.
So why let's say if I consider this substance done this process, it's only solved for rival.
Let's say at the second round.
Yeah.
At the second round, the first one.
They need to get the data information from the other one. So let's say in the round, the next round, I need to have the other.
Here's another example. So the first one, okay, the first one, you were saying the second block in the first line minimizes over its exponent.
Yeah.
Based on what the other one has said. And then on the third stage,
they're supposed to do the same, but in the next round, I need to get the data.
I mean, the point is, yeah, the point is the first one updates, and then it should be a second stage where the second one updates based on what the first one updated, without changing its own stuff. Well, I think.
It depends as well. Right? I mean, if the first one finishes solving it, it will get the new point, and the new point will be considered as.
Yeah, but the point is, why the first one is optimizing, the second stage, and the third stage, and so on are not changing.
Yeah.
Whereas here, it seems to me that they're changing. Maybe it's
they change. I mean, okay. This is not in control, but this is on a purely optimization, right?
no,
Okay. So when the first one solved, it's still considered the other one doesn't change. But when I go to the next step, because the other one they also have the newly solved solution, so they should send the information to the first one. So at the next step, the first one should know that what are the current or the previous choice of the other one, and just put it there. Might be because of my interest as well. And if we go to the case where the constraints appear, then because it's in the convex field, we can use a trick to want the feasibility by using convex combination of the feasible point. Let's say if I was previously stay at this point, and here I only have two subsystem 1 and 2. Previously I stay at this point, and subsystem 1 will optimize on this line only because it assumes that the subsystem 2 will stay at this update x0, and because system 2 stay here, then system 1 can only optimize on that kind of plan, on that line. And the next, when system 1 minimize the problem with respect to x1 only, let's say it can go to this boundary of the constraint set here. It should still be a peaceful point to the whole problem. The same to subsystem 2. Let's say if it consider that x1 would stay at this level, and it optimized with respect to x2 only, so it can only go along this line, and let's say it will end up here. So now two subsystems, they propose the two different points. Huh? They propose the two different points here. If we use the idea from the previous algorithm, then the next point that I consider should be this one. In the next step, I say, so now subsystem 1, I propose that I come to here, x1 come to here, subsystem 2 say x2 come to here. So this will be the next point for my iteration to continue. But because now there are some constraints, there are a couple of constraints, then this point might not be feasible anymore. So the idea that I cannot use this, but I can use any point between these 2 points. And using this, which means that I use a convex combination between these 2 points, and I end up in this line, and it's always be feasible. That is the main idea, to keep feasibility of my iterate. In the MVC setting, this work first introduced by Venkat in University of Wisconsin-Madison under James Rowling. Then after that, another PhD of James Rowling, Stewart, he extended Venkat's idea to the case when he wants to deal with more general couple constraints, but that requires transforming the algorithm from distributed to hierarchical, which means there needs to be some top guy to contact, to talk with all of them, the other guy, which we do not favor in the large scale setting. Another research that extends Venkat research is in CDC 2013 by Gross in Germany, that he provided a study on how to choose the best convex combination point so that it obtains the best convergence rate, which indeed does not change much. The convergence rate is still kind of the geometric convergence, but by choosing the different, but by changing the parameter, they can choose the point that leads the solution to the minimum, to the minimizer faster a little bit.